he will talk about the blow-up and turbulence.
Yeah, thank you. Well, I would like to thank Helena for the very kind invitation. It's a big pleasure for me to talk here. Well, I represent here our fluid dynamics laboratory that we have here in IMPA. And our interest in the laboratory, they cover the questions essentially of flows in porous media, surface waves, and this topic about turbulence is actually rather recent interest, so I got interested in that questions a few years ago when I moved to IMPA. Now, today I would like to review some of the results. So I'll be talking about shell models. So shell models is part of what we used to call toy models. So if there is some big, complicated phenomena, the logical way is to consider something very simple and try to obtain a playground when you can test your ideas and see what happens. So the shell models of turbines is one of such models, which was very successful in the sense that it's quite a simple model, and it captures a lot of the part of the turbines. It has anomaly, it has inertial interval, it has intermittency, all of this kind. Well, and the price for this is essentially that the shell model is almost as badly understood as the original Navier-Stokes turbine. So it is simple, but not sufficiently simple. But at the same time, recently there is quite a big part of advance in the shell models. So at least the basic part of what we struggled with Navier-Stokes earlier is existence, uniqueness, and the blow-up question are essentially understood in the shell models. So my talk I will first start with some introduction, but then I will talk about the blow-up in the shell models, and then about a very natural question of how this blow-up is related to the turbulence dynamics. So this is what is quite well expected. So the part of the blow-up will be, I would say, essentially rigorous theory, and the part of the relation to the turbulence is more like a play, essentially numerical, but we will see that the implications that we get from there are very interesting. So all the question is going around the Navier-Stokes equations, incompressible flow, and we're interested to understand the developed turbulence, which means that we're interested in what happens at the limit of high Reynolds numbers. And there are a lot of open questions. Essentially, any big question you pick up is an open one. So there is a question about uniqueness, existence of the solution with viscosity, without viscosity. Even if you take a question without viscosity, which is more important for turbulence, even there is no preferred answer if there is blow-up or no blow-up. So even this we don't have. But still, we want to understand the turbulence statistic, dissipation anomaly, so there should be some progress. The problem, of course, is very old. So the earlier questions is already more than 2.5 centuries old. But the language, as we understand nowadays the turbulence, it comes in a big part from the work of Kolmogorov in the Kolmogorov theory, famous theory from K41. Essentially, Kolmogorov introduced the notion of inertial range, of the viscous range, etc. So he got an idea that we can consider turbulence as something which has a universal isotropic homogeneous form, and ended up with the following description for the velocity moments. So he found that if you consider just dimensional, from a dimensional theory, you can recover the fact that the velocity moments, they should scale with a spatial scale r as a power law with p divided by 3. So this is the Kolmogorov theory. Well, it very soon was figured out that it's actually not correct, and this p divided by 3 should have a certain anomalous correction. And the idea where this anomalous correction comes, how to create theory, is till now the open question. Also, more or less a bit later than Kolmogorov, Onzage came to the similar conclusions, and in particular, he conjectured this dissipation anomaly, which says essentially that you increase Reynolds number, which means that you decrease the viscosity term, but the dissipation rate remains constant. And also he noted that if you assume all these properties of the system in this limit, then the velocity field cannot be regular. So it should be at least 1/3 Holder. And this directly relates the equation of turbines to the blow-up problem. So we need singularities in the flow, and the blow-up is just a question if the singularity appear in the finite time or it appears somewhat asymptotically, whatever. And all this fact that there is this anomalous exponents. Anomalous, in this sense, the most important part of the anomaly is this exponent. They depend on P non-linearly. It's not proportional to P. And the fact that it is non-linearly can be interpreted, for example, in a multifractal model. So if you want to get a velocity field with these properties, what you can make, for example, you can take several fractals with different scaling constants and put them on the top of each other. So if you want to create this kind of velocity field, you need to have an infinite number of fractals with a continuous number of scaling exponents. So very complicated structure. So now we come to the shell models. And shell model is an attempt to make it, well, the system as simple as possible. At the same time, we want to keep the inertial range and we want to keep the anomalous scaling. This model has quite a long history, and the model which is considered mostly in this context of the turbines is what's called now the Sabra model, which is some slight modification of the Gletser-Ohitani-Yamada model, which was developed, essentially it was developed by the year 89 from the earlier models. And it has this form. So what happens? First of all, we want to have small number of variables, which means that we just select some certain number of scales. So instead of the wave vector k, we consider just scales. So discrete wave vectors, wave numbers. So 2, 4, 8, 16. So we take them also in a geometric progression. So we have just discrete number of scales, and to each scale, instead of putting the whole velocity field, we just give a single number. And the important thing in that model is that this single number is chosen to be complex. So we take one complex number which describes characteristic scale of the velocities at this spatial scale given by the wave number 2 power n. And then out of these velocities un, we create an equation which contains as much information as the original Navier-Stokes. So essentially, this is the way how you can see that this equation it has all the scaling invariants. So this is acceleration, inertial term. Then we have a quadratic nonlinearity. The k corresponds to this derivative. Then we have a viscous term, forcing term, etc. And also the interaction is assumed to be local. So in this model, we assume the interaction of the un with two neighbors from each side. And what's interesting is that you push forward, like you assume that, first of all, you assume that there is same scaling invariance as in Navier-Stokes. Then we can assume that there is energy conservation, holistic conservation. You can also assume that it's Hamiltonian. So if you put this all together, then finally you essentially get to a single equation. So you even don't have a free parameter. So it's quite a restrictive series. So we end up with almost, in some sense, a unique shell model. And what happens with this shell model is it really has you can excite it at one side with a forcing range. It creates energy flow through its length, which dissipates in the viscous range. And surprisingly, the anomalous scaling exponents, they're all very close to the scaling exponents of the Navier-Stokes equation. So this is kind of miracle. It's even hard to distinguish one from the others. We will be okay. Some little different way to see this shell model is if we write the shell model in terms of vorticities. So instead of un, we take this ik and un and remove the viscous term of force, and we get this system. So this is a system which is quite a typical system in statistical mechanics. So we have an infinite lattice, and each lattice interacts with its neighbors, and the interaction is the same at all sides. So it's just it's same as we have, for example, in any statistical mechanics of one-dimensional crystal. Right? The only difference is that the interaction is not symmetric. It interacts with the right sides in a different way as it interacts with the left sides, and this is essentially what creates this preferred direction of the energy flow. But still, this system is turbulent, so its behavior is absolutely different from what we have in statistical mechanics, like in a crystal, for example. So now I'm coming to the blow-up. So blow-up problem is, first of all, the uniqueness and existence. So first of all, we need uniqueness existence for the full model. It will correspond to what we have for the Navier-Stokes. And we will be interested on the blow-up problem for the Inviscid model. So for this model where we remove viscosity. So for the viscous models, the global existence and uniqueness was proved in 2007. It was a work of Constantin Levantiti. Well, if we have initial condition for this vorticity field in L2, then we have global existence and uniqueness. So everything is very nice. So at least the problem, if you kind of project it to Navier-Stokes, it would correspond that for Navier-Stokes we have everything is okay. Now, for the Inviscid model, we know that there is a finite time blow-up. I will proceed like this. I will give a result, then I explain how the theory works, and finally I give some historical literature review. So the idea of how to describe this finite time blow-up comes back to Dobre-Gilson. This is a work of 98. Well, they positioned their work as a numerical, but actually the seed of the theory was completely already in that work inside, and with some polishing, it can become rigorous. So the result is the following. So if you have an initial condition in this space, then the system blows up in finite time for open set of initial conditions, and the blow-up solution is self-similar and universal. So it has, for large n times close to the blow-up, the solution becomes asymptotically of this form, which means that the velocities, they scale with the power, with exponent y0, this is 0.281. So the amplitude scale with this exponent, and times scale with exponent 1 minus y0. And here you can see the comparison of the real behavior. So these are how the amplitudes behave with time. The black one is a numerical, and the green one is this universal form. Even the shape is universal. So you see, for close to the blow-up, everything becomes fully universal. So how to understand where this universality comes from? The idea from the Dobre-Gilson was quite simple. So what you do for this system, essentially because the right-hand side is quadratic, you can do you can rescale speeds and you can rescale time. And when you do so, you come to the equation of this form, which is translation invariant, so it allows like kind of wave solution. And most important, it conserves the L2 norm. So it conserves the L2 norm, and this is essential element that allows to prove that existence of solution for all time. So there's no blow up in the renormalized system. You can global existence, uniqueness of the solution. But now this new system is made for the renormalized time tau. So when tau becomes infinite, so for all tau we have a regular solution. But when tau becomes infinite, it doesn't matter that t becomes infinite. Actually, the way around. When tau becomes infinite, t gets to the certain constant value, and this is a blow up time. And the machinery, how to make it, I didn't put the details, but anyway, what you do, you can introduce in a certain way the Poincare section for the system. And this Poincare map, if it has a fixed point attractor, it implies that there is a traveling wave solution, and the traveling wave solution, if you make this transformation back, it directly brings you to this form. So essentially, what is made in this using this renormalization is that you associate the blow up with the attractor of the certain well-defined system. So if you have attractor, like if you have fixed point attractor, then you have this self-similar solution, just this one. Say again? No. Speed. Actually, speed of the traveling wave can be any, because scaling invariants make it. You can get y0 is a property of the attractor. It's essentially y0. Let me see. Y0 is certain integral of it's an integral of certain constant over the period over the. Essentially, you can. There is certain integral that you can pose. It will be scale invariant, and it will just directly give y0. Well, I probably could. Essentially, this will be integral of this a over the period, where a is certain ratio of the. So let's. So y0 is the most important point. So we have just a single single exponent which describes every blow up. So here I would like to give some literature review. So of course the self-similarity was mentioned a long time because you directly see it in numerical simulation. So there was a lot of work mentioning this. Well, I also have to mention that there is a piece of work made for the dyadic shell models, and this is really rigorous, so you can prove that there is a blow up. The only problem is that these dyadic models do not show turbulence. But anyway, it's important to understand what happens. And the renormalization method, which comes back to Dobber-Gilson, so far we checked it for different shell models, which also correspond to convective shell model, the magneto-hydrodynamical shell model. It always works. So essentially, you can make renormalization. You can find Poincare map. You find the attractors of the Poincare map. If you find an attractor, you find the blow up. And the interesting is that blow up certainly doesn't have to be fixed point. It can be periodic orbit. It can be quasi-periodic. It can be even chaotic. So we have chaotic blow ups. And without this method, you can even not see it in the simulation. So all this works. And I would like to announce also the work of Gedert. This is our student in IMPA who will give a poster. So you can see this chaotic blow up directly on a poster. So well, this with that part, I finished the question about blow up. Existence, uniqueness of the solution. So that complicated part, which we don't have in Navier-Stokes Euler, here we do have quite recently, but this is already quite a step forward in comparison to the real hydrodynamic turbulence. So what we can now play around the question of what is the relation of blow up with the real turbulence. So this is always in the air, no? So we can try to see it. And this part of the talk is, there is nothing not much. Essentially, it's numerically based, so there's no theorems. But the idea is to see what we can, information that we can recover from from the fact that we know about blow up. So what you can see in this picture is a numerical simulation. It's a numerical simulation of the shell model with the 40 shells. This corresponds to Reynolds about 10 power 14. So this is why the shell models are so nice. You can hardly get this Reynolds number in any other system. And what you see is these lines are just amplitudes of each shell. So U7, U8, U9, U10, and so on. And you see the intermittency here very clearly. So there are windows of no dynamics, and then there is strong dynamics. And there is windows of no dynamics, strong dynamics, and so on. If you zoom any piece, it will be just similar. So there is but now we know that there is a blow-up. So there is a blow-up which has this structure, so some sequence of maxima. And you can see that all of these bursts, the turbulent bursts, they look like blow-up. So essentially, blow-up, which is universal, and it's a very attractive feature of the system with no viscosity. It shows itself everywhere in the real turbulent dynamics, so we can see it. Of course, it's not exactly blow up because there are many, they kind of interact with each other, so this is not exactly blow up. Essentially, even we cannot give a theory because in a theory we would need the norm to be finite, but in turbulent regime norm is that L2 norm already explodes. But anyway, what we can do is we can try to quantify the effect of these structures. So the idea, which is really a little naive, but it worked very well, is to identify all these structures just by looking at local maxima. So we take local maxima of each shell, and we connect the two local maxima if they come in increased time and increased n order. So we just make a connection. Boom, boom. And it turns out that we can separate all the local maxima in this way, in this curve, so just like we would do for the blow-up. And the first exciting feature is that 80% of maxima turned out to be in the sequences that start at a certain moment and go all the way down to the inertial range. So 80% of maxima is a strongly correlated information, very strongly so, because it goes all the way to the viscous range. These kind of sequences, they're called instantons. Well, this name comes partially from Dobre-Gilson, partially from Parisi. So this, but anyway, it's more or less. This name was here. So these structures we will call instantons. We'll not call them blow up because it's not a blow up, but it's similar to blow up. But so we give a different name, which is instanton, and they're created as a sequences of maximum. Now we can try to recover velocity moments. So we have velocity moments which scale with these anomalous exponents, and we can try to find these velocity moments in terms of maxima. So velocity moment is an integral. You have to average the moment over the time, and if you the main contribution to the integral is given by the maxima. It's kind of logical to assume. So you can rewrite this integral approximately as a sum of the maxima. And what you have, so finally we have a new definition of the velocity moments, but in terms of the sums of the maxima. So we do this. And it turns out that these new velocity moments, they also scale as a power law with exactly the same scaling exponent. So here, what is shown, the red line is the Kolmogorov series, the black line is what we have the dependence of the exponents on the order of the moment. For the shell model, the circles is what we have in this definition, so it's exactly the same. And the squares, if you take into account the sum only instantons, only those who are strongly correlated. So they also lie in the same line. So now we know that now we know that, okay, the instantons can be, so the anomalous scaling can be quantified in terms of these structures. So this is kind of logical. Okay, it's not very surprising, but it gives us a tool. There are some immediate consequences that didn't happen in Navier-Stokes. First of all, there are two, the first zero and the first scaling moment.
You're comparing this maximum you found against the whole thing. In that those red dots you're comparing against just the whole.
On the whole time simulation, we take all maximum everywhere, and we just put them in a sum up, and.
So the truth for you is numerical against numerical, and the truth would be the whole, just all the data you're getting from your simulation.
Yeah, we take all the data, extract all maxima, and instead of integrating over the whole simulation, we sum up maximum. And what we do, we construct the sums. Essentially, we construct the sums which has the same dimension as the initial integral. And it gives this exactly the same scaling law. So, well, you see, the integral, if you consider an integral in time, it's clear to assume that the main, especially for the intermittent, the main information is in the maximum of this function. So you recover maxima, you also recover the characteristic range of this maxima, and just sum up.
Okay, but the truth is just coming from all the data and the integral on the left-hand side?
The truth.
The truth in the sense that the KP that you're saying.
I'm not getting the code.
Say, what are you comparing? Yes, the answer is yes.
All right, thank you. Well, so the first two exponents, first of all, exponent psi 0 is 0. This is absolutely trivial effect because the zero moment is 0, is 1. But for instantons, it's actually it's not trivial at all. For the instanton, if you can, for the instanton, it's in terms of the sum, the definition, the zero moment is the sum of the time occupied by the instanton in the shell. And the fact that it's constant, it just means that the instanton are dense in the space-time. So this is first non-trivial implication. The second implication is that for psi1 now determines the rate of the instanton creation. So how many instantons are in each shape. So it's just sum over the ones. And it scales with psi1, and it's really how many instantons is shown here, and this psi1 is here. Well, so this picture shows the main result. So the main result is the following. So now we have the whole amount of maxima, which gives our scaling exponent, and the fact that the given those same scaling exponent is not so strange. But now what we do is, so we have different shells, 1, 2, 3, 4, and we consider maxima for the instantons that are created. Now, in that definition, we sum over all maxima. Now we will sum only for the maxima with the instantons that are created in a certain shell. So we put this conditional structure function. So we sum up over the maxima for the instanton created in a specific shell. What it makes is divides the whole huge sum into the small number of subsums, like each subsum for each shell. And it turns out that when you do this separation, the anomaly disappears. So this partial structure function, it scales as with a power which is proportional to p. with the coefficient y, which is 0.225, which somewhat reminds about the blow-up value. And this happens for all structure functions. It also does not depend which initial shell we choose, and it does not depend on P. So it's become absolutely self-similar. And this is actually the final picture. So here we have about 70 different structure functions collapsed to a single line. So it's six structure functions for something 11 shells. So you see that it's full collapse. So what we have is actually we found the internal structure of this sum. So if you divide the O maximum by the criterion where the instanton is created, everything becomes self-similar. Well, so you can push it forward. If everything is self-similar, you can start working with a probability density function. So this probability density function, which shows the probability to find the maximum of certain level in a certain instanton at the shell n, if the instant was created at the shell n0. You can assume that this is self-similar with the same scaling exponent, and it really does. So you can see here like around 10 to 15 curves, they collapse in the same curve.
So can we go back to the
Yeah.
I thought you're looking at the amplitude at shell n in time. What does it mean now created at shell
So yeah, this is important. So each instanton, it is start somewhere. So this sequence is start somewhere. So this is n0. This is level n0. And then we find the PDF, probability density function, of the velocities at the shell n. So we have two conditions, that it started at n0, and we look at the shell n. Just very simple criterion. So we have full self-similarity of the density functions, probability density function you can see here, and this red dashed curve is the curve that we will find analytically soon. So the result is the following. So we can take the whole amount of maxima, separate them in a rather small amount of pieces, and each piece is self-similar. It's not even self-similar, but all the probability density functions are self-similar, and they all are governed by the same exponent, just one exponent which works. Nothing. Yeah, you can think about this Brownian wave reaches the infinite shell infinite time. Yeah, actually, this renormalization method, it exactly maps it to the traveling wave. This is well, if we want to find this probability density function, I don't have time to give you details. So what we do? Well, this is just some derivations. Essentially, instead of the velocity, we take the logarithm, and instead of a probability density function, we just scale it in some way. And the idea is, using this self-similarity, we can come down to this relation. And this relation is just another form to write that we have a power scaling law for the structure function. So this is a power scaling law for the structure function with this anomalous exponent, just written in slightly different form. And for those who are used with the large deviation theory principle, this is exactly the relation to which we can apply the Gertner-Ellis theorem. So if we have this relation, that in fact, using the scaling exponent, we can recover the probability density function analytically. And in fact, the result is the following. So the probability density function for this transformed to already form, it should scale as chi n power minus ja, with minus ja is a rate function, and this rate function is nothing else as a Legendre transform of this Kolmogorov scaling exponent curve. So you take this scaling exponent, make a Legendre transform, substitute it here. So you find the rate function, substitute it here, you find this rho n, and then you find the full probability density function. So just for this curve, we can recover all these probability density functions. So it turns out that not only we split it into the finite number of self-similar pieces, but even the probability density functions, they're all universal. And they correspond, as soon as you know this curve, you know all the statistical properties. Well, this left figure just justification that numerical justification that this rate function really exists, because this red curve is what we found from by Legendre transform, and the black curves is a numerical data, so they just collapse to each other very nicely. Well, so up to now, what we discovered is the fact that the instanton dynamics is fully self-similar. So if we take instantons that are created in certain moment, they all behavior down there is self-similar and universal. So we have all the universal density PDF, we have a universal scaling exponent, everything. So where the anomaly comes from? And the only way the anomaly can come from is what the difference. So what the difference means how the instantons are created. So the creation mechanism. So you can see that when this instanton propagates, it leaves the tail of the energy, and this feeds new instanton, they feeds new instanton. So each instanton this kind of creates new ones. And since we are on a playground, so we can just take any assumption. It turned out that if you take any assumption of how the instanton creates other instantons, you directly come down to the anomaly. So you can even derive the anomalous exponents. If you give any statistical rule of how one instanton creates other ones, assuming that instanton propagate in a self-similar way, you directly come down to the anomalous exponent. So the anomaly in that picture is associated with the creation mechanism, while the bursts, they're fully self-similar. So that's an idea. And well, I think I finished. So I probably repeat the main messages. So first of all, the blow-up in shell model is linked to an attractor over an anomalized system. So it works so far for the most shell models, so we really can determine the blow-up by this attractor. By the way, it's interesting that you can apply it, for example, to the Burgers equation. It will be just the same. So also, it's a way how you can find the soliton wave in the Burgers equation. So if you go to the K-space and make this transformation, you will see that blow-up, even in Burgers, it has the same form. So as soon as we found a attractor, we know the scaling properties of the blow-up and the full structure of the blow-up. This is what we can do rigorously, and the rest is kind of idea how the turbines, what is the internal mechanism of turbines. First of all, we found out that this blow-up, it initiates some certain correlated structures, very correlated, and they're statistical objects. You cannot just pick up one of them. You will not see any self-similarity. But statistically, they're fully self-similar with a universal scaling constant. Then assuming this fact, we can show that anomaly of the scaling exponents is a result of the instanton creation. This is another message. And the third message is that we can, assuming all of this stuff, using the large derivation principle, we can analytically relate the whole instanton statistics to the anomalous exponents. So we can put them together. And this agrees perfectly with the numerical simulation. So you can see it right here. Well, and all these ideas is, of course, to give some hints of where we go in creating the theory of turbulence in the shell model. So the idea is probably to create some statistical theory of instantons, and which probably can explain turbulence in the shell models. But of course, this is not at all a simple question. But at least numerically we have an evidence that this is a possible way. So thank you.
Thank you. Are there some questions